Hi, I'm Daniel Winters, and this is Physics 2212, Lab 4, Magnetic Braking with Faraday. So, today we're just going to be exploring Faraday's law, and it's broken down into two parts, a physical experiment and computational model. So, some important physics principles to understand are Faraday's law, the Biot-Savart law, Newton's second and third law. They're all listed here, so you can pause here to take this in if you need to. So, physical experiment. When we did this, we dropped a neodymium or a neodymium bar magnet vertically through a um, roll of aluminum foil, and the whole point was to observe that as it fell through the aluminum foil, it created a magnetic field, but since it was moving, it created a change in flux. And due to Faraday's law and Lenz's law, this change in flux wants to be opposed by nature. So nature creates an opposing magnetic or produces a magnetic field that causes an opposing change in flux, and this, in the end, just makes the magnet fall slower. We found after 5 trials that the average time it took to fall from some height above the aluminum foil to some distance below it was 0.716 seconds. So these are some screenshots of some of the important parts of our coded model. You can see on line 97 starts the um, function to determine the magnetic field of the bar magnet, and on line 116 begins the function which calculates the change in flux or change in time. And then from lines 178 to 196, you can see our utilization of Newton's second and third laws. We used his second law to calculate um, velocity and position update vectors, and his third law to calculate net force. Now we're going to take a look at the output of the code. So first off, it's important to note that, like I said, how Lenz's law and um, Faraday's law mean that as it falls down through the cylinder, uh, an opposing magnetic field, therefore an opposing magnetic flux, are produced. Um, these come with currents running in circular rings around the cylinder, and that's what the colors on the output represent. So red is a counterclockwise current, blue is a clockwise current. Um, as far as the poles of the magnet go, it does not matter in the big picture which way you drop it, but as you see here, um, the blue is on top. If I were to flip the poles, then it would just flip the colors. So red would be on top, blue would be on bottom. Now for the time, it took in our computational model 0.225 seconds for the magnet to pass through the tube of foil, which I will call it a cylinder from now on. The reason it differed so far from the experimental value is because, like I said earlier, the experimental value was taken by dropping the magnet from some height above to some height below the tube while also passing it through the tube. It's also important to note the velocity versus time plot is linear. This implies that the net force over the system was constant, it was not changing. And because of this, we were able to solve for forces in the actual computational model itself. If I go back, or I won't go back, but we use Newton's third law to equate gravitational and magnetic forces to say they were equal. This is because if you add them up, they sum to zero. Therefore, there is a constant force. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Reducing the resistivity to zero would cause the opposing magnetic fields, therefore opposing fluxes, to meet in the center of the cylinder, and this would just cause the magnet to essentially levitate halfway through the cylinder. But because we live in reality where you cannot get, at least easily, cannot easily get zero resistance, it's just going to very, very greatly slow down the speed of the magnet as it falls through the cylinder. So the second what if question is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So, like I said, those colors on the cylinder were ring currents running through the perimeter of the cylinder as the magnet was dropped through. Now, if you cut holes in it, you can imagine it almost like that the perimeter is a circuit, and that hole would be a resistor in the circuit. And by adding this resistance, by cutting holes in it, it would cause the current, the magnitude at least of the current, to decrease. So, therefore, adding holes or slots would just decrease the magnitude of the current in the rings. That is all we have